this group. Okay, so they are doing this: teachers for environmental literacy, students for environmental. I can say this. It's actually youth, not students. So it's YEL, youth for environmental literacy. And they're having a meeting this afternoon from 3 to 5 if you're interested. Kaiser Happus. And you don't have to do it, but some people are interested. And so if you can't make this afternoon, because it was kind of short notice, I just found out about it yesterday, there's a Google form you can send in, and they'll send you updates. Totally voluntary. It's not going to hurt you or help you in here necessarily. And then I put the meeting Zoom link in there too. Again, it's at 3 o'clock. So if that's something that's interesting to you, check it out and report back. I'll maybe give you some extra credit. How's that? Woohoo! That's so the right.
You just do the thing, like, since I can't do the Zoom today. You just.
Yeah, show me they sent you back something and tell me about it. So that would be great. The mole is what we're talking about today. Now, we talked about moles briefly in October because of Mole Day, but we're going to get hot and heavy into it and why we really use it. It's not just to have a party, which of course we didn't get to have this year. Hopefully next year. Maybe next year you can stop by and check out our Mole Day party. Hopefully we can have one again. And so that's really all that's on the agenda for today. And because this morning got so crazy, I finally figured out what was going on with my laptop, and it's just PowerPoint, which is Microsoft, not playing well with Apple. So the new tech guy, it's a C. I can't remember his name. Cameron? No. Anyway, he figured it out. He did some research and came back, and I think we're going to be good going forward, please. So that is the plan. And then tomorrow we'll continue our discussion, do a little fun little activity with Sidewalk Talk. Yay, perfect for a Friday. Okay, I'm going to start out today like I did in the earlier classes to see if you paid attention on Tuesday and yesterday's assignments. So turn to your neighbor and tell them the difference. For those of you at home don't have a neighbor to turn to, what's the difference? How are they alike? How are they different? However you want to phrase it. Law of definite proportions and law of multiple proportions. Go.
Yeah. Oh yeah.
And Jack Conti, tell me about definite proportions.
So it's like you can't gain anything.
That's conservation of matter. Okay. Definite proportions. Taylor.
Is it like, so you have the atom and it can bond with one of the other things and it like stays like in, if you have like an amount of it, it's like proportionate to the other amount of it.
And it stays constant if you have the same compound. Okay. So definite means constant or same or however, you know. Amount's a good word. Ratio is a good word. You're always going to have hydrogen and oxygen in the same amounts, same ratios, if you have water. Okay, it's going to be a different proportion if you have hydrogen peroxide. Okay, but if it's a 2-to-1, well, those are atoms. If it's a 8-to-1 mass ratio or 1-to-8 mass ratio and a 1-to-16 mass ratio, because they did all these by mass, right? then you're going to have the right amount of the ingredients, the hydrogen and oxygen, to make those compounds. We're going to use the analogy of making a recipe a lot. So changing the proportions changes the results, right? Like I talked about with the brownies and the cake yesterday. Different proportions of hydrogen and oxygen give you a different result between water and hydrogen peroxide. But if you're going to have water, this is definitely the proportions you're going to have. Okay. All right, good. And how about the other one? Multiple proportions. Galilea.
The same two elements can go in different compounds.
Same two elements, or multiple elements. It doesn't have to just be two, but that's the easiest. Same elements, different proportions are possible. Too many letters. Same elements can go together in different proportions, and they make different compounds, right? Perfect. So hydrogen and oxygen, nitrogen and oxygen, all the crazy permeability possibilities of those. Okay? If you're going to have water, you definitely have to have the proportions 1 gram to 8 grams hydrogen to oxygen. Okay? But you can also have 1 to 16 if you have hydrogen peroxide. Same two elements. Good job, 6th period. Questions? Cool beans. All right, so there's a note in your feed, this one, that you can follow along on. You don't have to type on it. This isn't for points. It's not due. It's not graded, but you can type on this if you'd like as we go along. But I'm going to go ahead and jump into my presentation. Any questions from home? Okay, let's do this. So maybe, there we go. No. Hello, there you are. All right, so this is a crazy question. Could you count how many grains of sand in that sandcastle? Well, you could. Who would want to? But you could, I guess. It would take a long time, obviously. And, you know, if you're counting every single little grain. So those are things you can see. They're super tiny, but you can see them. Atoms and molecules, you can't even see to count them if you wanted to, okay? So there's got to be another way to do that. But we could count out 100, 1,000 grains of sand, find their mass, and then extrapolate it out to the mass of the whole sandcastle if we wanted to know how many particles were there. Why do we care about particles? Obviously, we don't care about sand and sandcastles, but when you do chemical reactions, it's particles, it's atoms and molecules coming together, and they have to be coming together in the right proportions to be able to do a chemical reaction. Sometimes you'll have leftovers, just like when you're cooking. Sometimes you won't have enough stuff in your pantry, and so you'll have to cut the recipe somehow in half or whatever. But knowing how many particles is critical to doing chemical reactions. All right, how do we measure things? Well, again, we can measure them by counting numbers of things, like the numbers of nails or screws or whatever these are in this box, probably 100. That's typical. We could do it by mass. You know, when you go buy birdseed, it's probably by the pound, but we would use kilograms, of course, and you could do volumes. So for liquids and gases, a lot of people forget that gases are how this whole conversation actually started. In the late 1600s, early 1700s, people were realizing that gases were matter and they had to do something with them, and they had mass. And so a lot of these early concepts, including Avogadro's hypothesis, had to do with volumes of gases and numbers of particles. So those are the 3 ways, okay? And we're going to learn how to do all of them. The most important one in a real live chemistry laboratory would be the mass, unless you were dealing with gases. We're not going to count atoms very often. So if you want some paper clips, or you're a paper clip manufacturer, you're not going to have someone in the back room counting out 100 paper clips and putting them in each little box, right? To put up paper clips in a box, they do it by weight, by mass. So we know how much 100 paper clips should weigh. the little box goes down the conveyor belt. It's got a little sensor underneath, gets underneath the filling funnel and in go the paper clips. Oh, yep, that's the right mass. And off it goes down to get packaged up further. Same thing with like chocolate chips. Got to bring in chocolate, right? So there's nobody counting how many chips are supposed to go in the chocolate chip bag. How come? They'd eat them all. Okay. Yes, it would take too long. So they do it by mass. Okay. And that's what we're going to do in here. But we have to learn a little bit more than that too. All right. This is a really goofy example. It's a super simple one. Get out a calculator if you have one. Well, maybe you could do it in your head. I don't know. We're going to go through this example. I'm going to talk you through a couple of different ways to approach the problem. There's more than one. And we're using something relatively familiar. Everybody knows what an apple is. Yeah, it's just to try and make the concept. You're going to have to make the conceptual shift to atoms and molecules. But for right now, we're going to talk about atoms. All right, here we go. Okay, somebody else talk. I'm tired of hearing myself talk. Logan, would you read the prompt, please?
What is the mass of 90 average-sized apples? If 1 dozen of apples has a mass of 2.
Beautiful. Okay, so in every problem, there's two things. There's the given information and the asked for information. And I'm going to make a big deal about these terms. Your book calls them wanted and known, but I go with asked for and given because that's how I learned it, and it flows better for my brain. So what is the problem asking you for, Galilea? It's your lucky day. Absolutely. So question is mass 90 apples. Beautiful. And what information have they given us? Marlene, I don't know if you can text in. How about anybody in here? What information did they give us? Beautiful. 1 dozen apples. Okay, so we're going to do something called dimensional analysis, and it's a trick to keep all your units straight. We're going to use horizontal fractions, not slash line fractions, even though we usually say per and stuff. And dimensional analysis makes use of something called unitary rates. And all that means, that's this fancy math talk for the top and the bottom are equal. The whole fraction equals 1. Have you guys heard this before? Any of it? One person has. Anybody else? That's it? Okay, so there's 2 ways I could use this. Right? You know about dozens, right? Sometimes you multiply by 12. Sometimes you divide by 12. So 1 dozen per 12 apples in this case, or 12 apples per 1 dozen. 1 dozen is 12. That number is 1, right? 12 is 1 dozen. That's 1. And these are also equal to each other. Sometimes we're going to divide by 12. Sometimes we're going to multiply by 12. Okay. So in this case, there's multiple ways to start this problem. I just wanted to set you up with that. Go ahead and talk to your neighbors and see how you're going to get going on this. What would be the first thing you do? I'm not asking you for the answer. I'm just asking you what would you do first, what would you do second, that kind of stuff.
Yeah. Yeah, 7.
So 7.
And you have 6 left over.
All right, so you guys are plunging right ahead. So Lauren, tell me, what would you do first? Everybody, every single period, that's what people want to do. 90 divided by 12. How come? How many what? Dozens, yeah. So here's the deal. In math, you just have to worry about numbers. And here you have to worry about units. And keeping your units straight, top and bottom, is going to really make your life easier. So what she's doing is taking the 90 apples divided by 12 apples per 1 dozen. Everybody agree? Okay, so that's this one, right? No. Here's the trick. What she's doing is, normally we would just say 12 apples per dozen, right? We probably do a little slash line instead of this horizontal thing. If you divide, let's see if I can do this right. Here, I'm just going to get this one out of the way. If you divide two numbers, you'll get a number for your answer. But you can, just like in division of numbers, you can cancel units as well. Units on top, cancel units on the bottom. Okay, so you get what, 7.5? Okay, that's the number for these two numbers. But then you've got per 1 dozen, per a dozen. Kind of weird, right? So if it's a denominator in the denominator, where does it go? Anybody? What's the opposite of the denominator? Numerator. So it's going to end up being 1 dozen. So it's actually, and you know how to do this in your head because you know all about dozens, okay? Here's how to set it up when you're dealing with atoms and molecules and moles, because it gets really confusing. For sure, I know that. Okay, 90 apples times, what are we trying to get to? Dozens, apples, dozens of anything, right? Okay, so this is what she said. She said, take 90 and divide by 12. She's absolutely correct. There's nothing wrong with what she said, okay? But I want you to see how to set this up for yourself when we get to stuff that's more complicated. Make believe that any number that doesn't have a denominator is over 1. And set everything up horizontally. Apples on top, cancel apples on the bottom. And if we stopped here, this would be the answer. But that's not what it's asking for, right? So what's the next thing we have to do? It's asking for a mass, not a number of dozens. So Gwen, what's the next thing we're going to do?
Multiply the 7.5 times 2 kilograms.
Absolutely. So 7.5 dozen times 2.0 kilograms per 1 dozen, right? Oops, I did this wrong, didn't I? Ha! I should have had, this is fine. I mean, there's nothing wrong with that, but this is the next one here. This isn't the same unitary rate, my bad. So you could do 2.0 kilograms. Sometimes you have to multiply by 2, like this one, or sometimes you would divide by 2, right? I could give you a mass and ask you how many apples you have, how many dozen. So again, the units on top can cancel the units on the bottom. This is understood to be over 1. You're left with kilograms in your answer, which is what the problem originally asked you for. Now, the cool thing with that is you can set all these things next to each other. So this is how many apples we have. This is how many things in a dozen. This is the mass of a dozen apples. Okay. And so from here, we can cancel dozen with dozen. We're left with kilograms. 90 times 2 divided by 12. 180 over 12 is still going to give you the 15 that the answer is, right? Okay. So there's ways to do these problems. I want you to get in the habit of doing them, like these long horizontal fractions. And it'll probably be better to do that on paper and with a pencil. So I could also have figured out, doing this, I could also have figured out that 1 kilogram, right? 12 apples per 2 kilograms is the same as 6 apples per 1 kilogram. I could do that way if I wanted to, but I don't. And I could also do one other thing, okay? There's always more than one way to solve math problems, unfortunately. So I could also set up a proportion, right? And still come up with the right answer. So 2 kilograms per 1 dozen, which is 12 apples. So I already made that conversion on my PowerPoint. Is the same as X kilograms per, what did I just do? Did I do this wrong? No, 90 apples. There we go. End of the day, brain fart. Okay, so then you do, multiply both sides by 12 and multiply both sides by 9. You can do all your regular algebra stuff, or you can do the cheater's way, right? And do cross multiplication. And you still get the same answer. Okay. Does anybody think to do a proportion like that? Okay. So again, there's more than one way to do these. It's okay. But try and get in the habit of setting them up in a big string. It'll save you a lot of headaches later on. All right, there are words that mean numbers. Obviously, a dozen means 12. There are lots of words that mean numbers, and some of them you know, and some of them you don't, and some of them are for specific things. So most of us know that a decade is 10 years, right? I'm not going to say have a decade of pens. It's kind of silly. But anyhow, but two things. You have 2 shoes on your feet. A pair. Yeah. 12, we already know is a dozen. And then this one's kind of weird. It comes up on the video too. A ream of regular weight paper. Anybody know how many sheets of paper that is? Really important trivia. 500. Good job. Okay. And then no one's gotten this one yet. So congratulations on getting the ream. One other person did. 144. That's 12 squared. A dozen dozen. Anybody know what that's called? Don't use it very much. That's called the gross. Why? I don't know. 13. One more that the baker ate. I don't know. Yeah. Okay. But of course, we're not talking about dozens and baker's dozens and donuts and stuff like that. Darn. We're talking about moles. And of course, a mole for a chemist is the amount of substance that is 6.02 times 10 to the 23rd particles. Could be atoms, could be molecules, could be ions, could be formula units. There's all different things. A mole of anything, and that comes from the Latin for pile or heap, which is what moles do in your garden, make big piles of dirt, is 6.02 times 10 to the 23rd. It's a ridiculously huge number, incomprehensible, truly, as you'll see soon. It has been agreed upon in international chemistry circles that is exactly the number of particles in exactly 12 grams of carbon 12 atoms. Carbon always has 6 protons. Carbon 12 has how many neutrons? 6, yeah. So there are other types of carbon. Remember, there's carbon 13, there's carbon 14. But carbon 12 only has 6 protons, 6 neutrons, and the appropriate electrons, of course. So if you have exactly 12 grams of carbon 12, you have exactly 1 mole's worth of a substance. And that is the unit of measurement of particles in chemistry and the Système International. Okay, so we're going to watch this little clip. Just really fast, the term representative particle is used in your book, and it gets silly. It's silly. but that's what they use because sometimes it's atoms, sometimes it's molecules, sometimes they're ionic compounds that have formula units, not true molecules. And also very important in solutions, we measure how many ions are present in solutions because that changes the behavior of the solution. So we'll use RPs, representative particles, in our calculations, but we'll come back to that. All right, questions right now? We're not going to get very far because, yeah, this morning was terrible. It was terrible. What's that? Oh, relaxing music. Yes, yes. We need some relaxing. That's why I put it on. Because I needed to relax. All right, here we go.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it.
Ew.
Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in the container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea. Scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help.
So just really quick, this is 18 milliliters of water, mostly. That's a mole's worth of water molecules. Okay, and he said teaspoons. It's really, no, that is teaspoons. Yeah, it's like 5 milliliters per teaspoon. So not very much. Okay. On the other hand, this is a mole's worth of sugar. Glucose. This is actually sucrose, table sugar. Okay, and all of these have a mole's worth of zinc, a mole's worth of copper, a mole's worth of iron, a mole's worth of aluminum. Did I count out all those atoms? No, it's not possible. I massed them. I got their mass, their weight. Okay. And that's how I know how much is there. All right. Let's just go with this.
Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
So if I want to make a salami sandwich, though, you decide how many pieces of salami would go on your sandwich, right? It depends on how big it is and whatever, but you would not probably put the whole quarter pound of salami. Maybe you would, I don't know, on your sandwich. Hard to know, but you buy it by the pound. You buy it by mass, and then the particles get to make sandwiches. You get your chemicals by grams, and then the particles get to make molecules when they react. Okay, so hopefully that makes some sense. What we're going to do tomorrow is learn more about how we actually figure out how many moles of a substance we have. And we're going to do that by drawing on the sidewalk. Perfect thing to do on a sunny Friday, right? But for your education too. All right, like I said, this morning went terribly, so I am not going to go any further today. Any questions right now? Beautiful. You've been a lovely audience. Thank you very much. Have a wonderful rest of your